Hello everyone. Today we are going to discuss about theory of estimation. And among the theory of estimation, there are two chapters. The theory of estimation is divided into two chapters. First one is point estimation. Second one is interval estimation. The chapter point estimation has already been covered in the previous video, but I want to apologize for the fact that the video was not made that. I mean, the quality of that video was not that good. I seek your forgiveness for that. And today we are going to discuss about interval estimation. Now, you may wonder and ask that even if we have already found out how to find estimation or estimator of any event or any distribution, why do we need to have another estimation, or why do we have to have the interval estimation if we already have point estimation? And I would answer that question by saying the point estimation, if you had seen the previous example or previous video, you might have noticed the estimator that we have that the estimator that we had made for estimating some of the values of the distribution uh, was not able to give the accurate answer. So that's why there was a lot of variance there. So to overcome that problem, if we introduced or if you introduce if we introduce a method of estimation which does not give the answer of the estimator in a particular value, like point estimation, but rather a interval. If the formula could give us a interval of estimation, then it would be easier for us to keep track of the variance and the difference from the true value. Okay, so that is the first notion that gave birth to this interval estimation. Okay, so uh, now interval says that this is the original value, this is a true parameter, and this T1 is the upper boundary, sorry, the lower boundary, toe bound, and T2 is the upper bound. An interval such as this, which estimates the unknown parameter population, an unknown population parameter, which is theta, with a certain probability, is called an interval estimator. This is the definition of interval estimation. Now let's see what it has to say about that. Okay, so it says that the probability that this theta lies, okay, you can't see there. Okay, the probability that the true parameter lies in between T1 and T2 is given by 1 minus alpha. That is 1 minus level of significance. Okay, now what does this mean? One minus alpha gives us the confidence level. Okay, it is called confidence, also known as and confidence level, and so we can say this interval of T1 to T2 to have alpha level of confidence. Okay, so it's alpha level confidence interval. Alpha, oh yes, we can say that. Let me have a better look at it, okay? Okay, one mistake that 1 minus alpha is not confidence level but confidence coefficient, which is actually probability, which is just probability, okay? So, so to interpret it, what we can say is there is 1 minus alpha probability that theta, which is the unknown true parameter of the population, unknown parameter, which is the unknown parameter of population, there is 1 minus alpha probability that an unknown parameter theta would lie in between T1 and T2. Okay, so that means there is 1 minus alpha confidence that we can say this estimator T1 and okay, we can say a scientist has a 1 minus alpha confidence that this theta would lie in between T1 and T2. I think I was able to make you understand this. So this is what the notion of 1 minus alpha and the interval estimation is. Okay, if you want to measure confidence in terms of a percentage, then you can say that you are 1 minus alpha times 100% sure that theta will lie in between T1 and T2. So this is the interpretation of all of this. Okay. Now let's talk about how can we construct these confidence level. Now there are two methods for constructing a confidence interval. First one is called pivotal method. Second one is called maximum likelihood estimator method, MLE method. Okay, now let's see both of these. Okay, so let's take an example. Using pivotal method, find 100 times 1 minus alpha percentage confidence interval of statistic Z. I don't know why, but every single time I have to read that out. 100 times 1 minus alpha percentage, I always get stuck and I couldn't say this. So for that, let's just for my convenience, let's say this to be k percentage. Okay, if you could digest it, that would be very helpful for me for this entire chapter, just to say it k percentage. So let's say this to be k percentage. So using pivotal method, find k percentage confidence interval of statistic Z. Okay, now Z is equals to T minus theta root under Vt. This is our Z statistics. Now we have to find out by using pivotal method. Now what is a pivotal method? Now pivotal method is a statistical method that introduces a term pivot, and it says us to find a pivot such that the intervals that we get for our function shouldn't have this interval for our estimation shouldn't have any unknown terms, unknown parameters. Okay, any unknown parameters. This is what the pivotal method or pivot means. Now we have our statistics Z. Now Z involves t minus theta by root under Vt, where these t both are the known terms, but this theta is an unknown parameter. This is an unknown parameter. So how can we write this in terms of just the known term? And that would be like this. For example, if we could just make this theta alone, then that would be z times root under Vt. Yes, Vt t minus theta is equals to this. Then add theta to the both side, that would give us t equals z root under Vt plus theta. So if you want to make theta alone, it would be t minus root under Vt. Okay, so we got this term. This is the term which does not involve any of the unknown terms. So that might be our function, our pivot. Okay. Now pivotal method involves two functions only in known terms. So first one is this. What is the second one? Now you might have already guessed it. The second one may look like t plus z root under Vt. So let's consider this to be psi 1 of t, because everything is just t. Let's consider this to be psi 2 of t, because everything constitutes t. That's why we got an interval which looks like this: psi 1t theta psi 2t. This is equal to t minus z root under Vt theta t plus z root under Vt. This is what we get as interval. This is interval. It is 100. Okay, just I had already said it. It's K percentage confidence interval, and we found it by using pivotal method. Okay, this is how we do it. Now again, you might have already noticed it, but just for the sake of completeness, we can say that the probability that theta lies in between these two intervals is what? 1 minus alpha. Okay, so this is all about pivotal method. Let's directly go to the another examples of some popular and most useful confidence intervals, distributions, and let's find out their confidence interval. Okay, so first of all, let's talk about confidence interval for the mean of normal population. Mean of normal population. Okay, so as you already know, in the normal population, our statistics is Z, which follows the standard normal distribution, and G is given by x bar minus mu by sigma. So this is the statistics for the normal population. But if we consider that we take not directly or not the normal population as a whole, but we distinguish the normal population into small samples. If we separate a single population into different samples, then the Z statistics or Z score get modified. Now, how do you think this is going to modify? So, if we consider n to be the sample size, then our Z score for the samples which follow normal population would look something like this. Now, as we have got our G score, now we can apply our pivotal method to find out the confidence interval for this. So, as we have already discussed, the pivotal method. This pivotal method involves making a function only in the known variable. Okay, that doesn't depend upon unknown variable and only depend upon known variable. Then such kind of pivotal function, such kind of pivot making process is called pivotal method. So how can we make pivot? How can we make a pivot out of it? So let's suppose psi that depends on, okay, so as I have already said, pivotal method, we try to choose pivot which is only consist of which is a function of the known variable. But if you see here in the G score, what do you think is the known variable and unknown variable? So n, x bar, these are sample attributes. Okay, when you have a sample from a large population, then you know the sample mean and you also know the sample size, but you don't know the population mean. That's why population mean here is the unknown variable and other are known variable. Now you might have already guessed that sigma is also a population parameter. Okay, so we cannot say sigma to be a known parameter. Now when we have two unknown parameter, then we can't write a pivot only in the known function. It will definitely involve some of one of the unknown variable too. For that, let's suppose the sigma is known for a while. Okay, let's suppose say sigma is known. If sigma is known, then we can write the pivot in the following form. Pivot of what? X bar as sigma is given by, actually, even though the sigma does not involve any kind of unknown function, but the notation of it involves the unknown function. Okay, so it looks like this. Now this is equals to x bar minus mu by sigma by root n. Now let's try to find out the pivot. Actually, what we have to do here is, according to pivotal method, we have to find out one of the function, pivotal method of pivot function, which is smaller than this, and one function of pivot which is greater than this, such that the pivot here lies in between psi1 and psi2. So let's try to make to form that kind of things, that kind of intervals. So first of all, what we can do is, what is unknown here? Mu. So let's try to separate mu from the known variables. So for that, we can multiply this, we can cross multiply sigma root under n, and on addition of mu on the both sides, you get mu equal x bar minus g sigma by root under n. Okay, this is what we get. So this here act is the lower boundary, so we can write psi1 of x and psi1 of x is equal to x bar minus g sigma by root under n. Now what do you think the second function or the upper boundary of this interval look like? Now, as you might have already guessed, we have plus in place of minus, and this here act is the upper boundary. So now the interval, confidence interval for mean of normal population looks like this. Okay, so this is our confidence interval. Now if you want to see it visually, suppose a normal curve. Okay, suppose a position of mu x bar minus z sigma by root n. Now this here act minus z by alpha minus z alpha by 2, and this act is plus z alpha by 2. So this minus z is defined by this boundary, plus z is defined by this boundary. Okay, and if you want to know the probability that our original unknown population parameter lies between these two boundaries, so that can be proved by taking the probability of this thing. Let's suppose this to be x, capital X, and this, if it is equal to the probability of 1 minus alpha, then it is proved that our mu, which is unknown population parameter, lies in between minus z alpha by 2 and g alpha by 2, which are the boundaries. Okay, so this is how you're gonna find the confidence interval of mean of normal population. Okay, so let's see some cases, special cases of this kind of confidence interval. So let's suppose instead of population variance, we don't know population variance. So the first case or the first situation that we have defined was sigma is known in g squared, x bar minus mu by sigma by root under n, right? Now let's suppose for the time being that sigma is unknown. What do you think would be the appropriate method to find out the confidence interval in that scenario? I think when I was discussing about the pivotal method, I had stated a fact that if we don't have the particular value or the particular variable, and it is unknown unknown in our sample, then in that case we can estimate it by using unbiased and sufficient statistics of it. For example, if there is something, for example, let's suppose y let's suppose y is an unbiased variate, unbiased as well as sufficient statistics for y, for sigma. In that case, what we might have to do is that we are going to neglect this sigma and we are going to write y instead, because expectation of y, that means if we have y as a variance in our sample, then it is equal to sigma, which is population variance. Okay, if such kind of statistics exist, then we don't have any problem even if some variable of the statistic is not known. So that's why we can say that. Now it turns out that in statistics, the variate that defines a sample variance actually exists, and it is not y but rather s squared. Now s squared is called sample variance, and it has its own formula, which is s square is equals to 1 minus n minus 1 summation xi minus x bar whole squared. This approximate to 1 by n summation x bar minus x bar whole squared if n is sufficiently large. Okay, so this is what we have that can approximate the population variance. Now I'm not going I'm not going towards that right now, but I will come to that point later. But before that, since we have already found out, I think I should go there, right? Okay, yes. So now if we have this, what do you think would be the Z statistics? Now Z statistics, wait a minute. Yeah, so Z statistics now would be x bar minus mu by s over root under n. Okay, so if we have this, then our confidence interval becomes x bar minus g s by root under n x bar plus mu, x bar plus g s by root under n. This is our confidence interval. Actually, it is also known as 100 times 1 minus alpha percentage, but it is too hard to say every single time. That's why I call it k percentage. Now again, as a disclaimer, it is not in a standard term to say to be a k percentage, but we can say that for the time being. Okay. So for confidence intervals, a more standard form or more better way to say this is that k percentage confidence interval is given by this. Sometimes we can also see this to be written as this, so don't get shocked when you see such kind of things. Okay. Now as we have all so I think you had noticed something, and the thing is we considered for s to be 1 by n minus 1, sorry, s to be 1 minus n from s equals 1 by n minus 1, we consider a thing, that is n must be sufficiently large. What if n is not large? What if we have a small sample, not a large sample? And small sample size, when we have a small sample size, then our approach of taking it will be different. So even though our population, even though our population follows normal distribution, if we have a sufficiently small statistics, then this is not said to follow the normal distribution, but rather a t distribution. So our statistics would be a t statistics, not a g statistics. So t statistics would be x bar minus mu by s by root under n. So our interval would be minus t alpha by 2 to t alpha by 2. This would be our confidence interval. Now in place of t alpha by 2, it would be x bar minus t alpha by 2 s times root under n this. So this is going to be our confidence interval. Okay, wait a second. Yes, so this is going to be our confidence interval. But now, as we know, this t alpha by 2 also refer that it has n minus 1 degrees of freedom, so we have to write this in place of this. So a more appropriate way of writing it is this. This is the confidence interval. Okay. Now this is all about the confidence interval for mean of normal population. Now let's go towards the confidence interval for the difference between means of two normal populations. It is pretty similar, but instead of one we have two variables now. Okay, so same thing, confidence interval for difference between means of two normal populations. Case first, large sample size and variance is known. Same thing. Okay, so we have z equals wait a second. Let's suppose confidence interval between means of two normal populations. So let's suppose two normal populations n follows 0 to 1. Okay, instead of assuming that this is a standard normal distribution, let's suppose it to be a generic normal population. For example, mu with mu1 and variance sigma 1 squared. And this is a population 2. This is a population 2 and follows mu2 sigma 2. Okay, now yes. Okay, yes. So what do you think? What would the difference in between the mean? So difference in between mean would be mu1 minus mu2. And what do you think the difference in between variance is? Actually, let me check. Okay, yes. So we have two normal populations. Now what do you think is our goal? Our goal is to find out the confidence interval for the difference between the two means. Let's suppose we have two samples, population means of two normal populations. Okay, so let's suppose the mean of this sample is x bar. Let's suppose the mean of the another sample in the another population vy bar. If we have that, then our variate for which we want to find out the confidence interval would be x bar minus y bar. Now it is going to assume the population variance, the difference between the population variance. If you remember, we had z score, which looks like x bar minus mu by sigma by root under n, right? Now we have x bar minus y bar. So what do you think the z score for the difference would be? So instead of saying yes, z score would be x bar minus y bar minus mu1 minus mu2 by sigma by root under n. So sigma 1 squared by root under n 1 plus sigma 2 squared by this root under n2. Is it true? No. Is it true? Okay, so we can also write it in the form as a whole, like this. Okay, so let me check. Yes, we can write the z score in this form. Now use this to find out the confidence interval using pivotal method. So this is our z score. So our interval would be minus g alpha by 2 z alpha by 2. So here we have to write x bar minus y bar minus g alpha by 2 times the whole thing is sigma 1 squared plus by n1 plus sigma 2 squared by n2. This is plus minus smaller than mu1 minus mu2. Okay, so this is going to be the confidence interval for or differences in between means of two normal populations. What if we don't know variance? If we don't know variance, uh, we can use S1 and S2, and I have already discussed what is the reason for using that. Alright, so now what if the sample size is small? So if the sample size is small, then we can use the same method that we used earlier to assume that the sample does not follow normal distribution but rather a t-distribution. If we do that, then we would get the t-statistics, which looks exactly like this, but these becomes S1 and S2, and this becomes T alpha by 2 and sorry, not alpha by, yes, T n minus 1, and then we can write that in terms of the exact same uh, confidence interval. The confidence interval for that, for the small sample case and large sample case, looks exactly like same. Okay, exactly the same. So this is all about it. Let's talk about confidence interval for population proportion. So for constructing confidence interval for for a population proportion, we need to understand the meaning of proportion first. What do you think is proportion? So let's suppose we have a sample. Let's suppose we have a normal population and we took a sample. Let's suppose the sample size is n, and let's suppose we have let's suppose the items with certain characteristics be x, other be n minus x. Then let's suppose the probability of getting items with certain characteristics is given by x by n, right? So this is what called the sample population. Sorry, sample proportion. The number of things with a certain characteristic by the total number of things in a sample is called a sample proportion. Similarly, the number of things with a certain characteristics given the total population in a population is called population proportion. So we have defined small t and capital T. Small t refers for sample proportion and capital P refers for population proportion. Okay, so we need to construct an interval for them, for the population interval, population proportion. So that would need some pivot, and the pivot, this case, looks like P by n. Is it so? Okay, actually it's, yeah, it is analogous to the fact this sigma is equal to root under PQ. Now here PQ by n refers to the population variance. It's sigma by root under n, here refers for sample variance. Similarly here, not the population but sample variance. So in proportion case, capital P, capital Q by root under n gives us the sample variance. In our case, sigma squared by n gives us the sample variance. Okay, so this is very analogous to this original equation or original pivot, or we can say statistics. Okay, so now what we're going to do is we're going to say this to z. So the interval would look like from minus z alpha by 2 to plus z alpha by 2, and it would look like p minus this times root under pq by n z alpha by 2 this. Alright, so this is what we need as the confidence interval. Now if we want to find out the confidence interval between the two of the population proportion, it is very easy, and we can do that just like in the previous case as we did in the difference in between the means. Okay, so I'm not going to do that because the concept is same and you know how to do it, so why should I waste my time? Let's talk about building or constructing confidence interval for population variance instead. Okay, so let's suppose we have now. Okay, one thing you should understand is up to now we are talking about up to now, and even until I say explicitly that it is of the district this is of the population is of different distribution, until then the whole thing that we are doing is just for the cases of normal population, just for the populations which are actually normal. That means the samples are taken from the normal population. Okay, so just keep that in your mind. Let's talk about confidence interval for population variance. Population variance. So we know okay, so we know the sigma actually. Okay, yes. Let me check. Okay, so now this is quite interesting. Confidence interval for population variance. Okay, so the point estimate. So we need to write the point estimate of variance. Now point estimate of variance. Point estimate of population variance. Let's suppose this to be sigma this. Maybe if you don't want to write the same symbol, you can just say what? Which letter do you like the most? Maybe summation? No, summation, no. Let's suppose anything, come on. Maybe alpha. Alpha means the level of significance. Beta also have its own thing in probability. What do you think? Come on. Let's consider this to be D. Okay. So let's suppose the point estimate of population parameter D is equals to 1 by n summation x bar xi minus x bar whole squared. Alright. If now this, okay, so we are talking about population parameter, right? So this would be x bar xi x bar minus mu. x bar minus mu whole squared. Yes. So this is our point estimate for population variance. Now we know that this is actually population variance, right? So we can say that we can say that the interval estimate of sigma squared can be established by defining a statistic or a pivot which is given by d sigma squared is equals to summation I equals 1 to n x bar minus mu by sigma squared. Okay, now this can also be written as n by d sigma squared, no, sigma squared by d. That means our pivot, which is defined by this pivot. Now if you see this pivot, then you can notice that this is actually summation from I to n of square of the normal variate zi. So what do you call this kind of distribution? The distribution which involves the summation of a squared standard normal distribution, standard normal variate, then it is called chi-square variate. So we can say that the estimation of the population variance follows the chi-square distribution. If it is so, then we can write the confidence interval now in the following form. Confidence interval for the population variance would be chi-square variance minus chi-square plus chi-square alpha by 2 alpha by 2. Now how do you write that? How do you think we are going to write that? Yes, so we are going to write it in this form, and that is chi-square minus of n d by sigma squared and d by sigma squared. Okay, now the sigma is replaced by minus is changed into psi square alpha by 2 psi squared and d by this is changed into psi square 1 minus alpha by 2. Okay, now this d is actually written in this form in standard notation, so we can change it by writing it in this way. So this is what the confidence interval is. Now the probability of this would be equal to 1 minus alpha. This is quite interesting, and I personally also didn't get that very well. Okay, now it says that if we have if mu is unknown, then we change this confidence interval very subtly by putting n minus 1 in place of n and s squared in place of sigma, estimated sigma squared. And this is all. This is all the changes that we need to do, and the degree of freedom is n minus 1. Since it follows the t distribution, the statistics follow the t distribution if we have small samples. Okay, so this was all. I didn't get that well, so I couldn't explain it that well, but is good. Okay, so this is all about it. Now there are a lot of other topics too, but since they are not in syllabus, I don't think it is very important to discuss. Okay, so okay, up to now we have discussed about creating confidence interval by using pivotal method. But if you remember the first lecture, then I had said there are two methods for constructing confidence interval. First one is by using the pivotal method. Second one is to follow maximum likelihood estimate method. So you may be wondering that I haven't talked about it up to now. So so that's why now I am going to do that. Just I'm going to take a single example of it, and I'm going to do this. Okay. So yes. So if we take a random sample from a distribution and let's suppose theta is a parameter that has to be estimated. Let's suppose theta not bar but theta hat is what we estimated the theta to be. If that is so, then by using the large sample property, and okay, the most important thing is the sample that we have chosen for this kind of MLE evaluation, or for constructing confidence interval using MLE, that must be large sample. Okay, so by using the large sample property, we can estimate a test statistics that is given by z equals by root under variance of theta. Okay, theta estimate. So this is our test statistics. Then this follows the standard normal distribution n tend to infinity, where variance of theta estimate is the minimum variance, and it is given by this minimum variance is given by 1 by Fisher's information, and it's equal to 1 by minus expectation of d log L by d theta squared. Okay, now for constructing key percentage confidence interval, we can write minus g alpha by 2 g alpha by 2, and that is given by theta minus theta root under v estimate theta minus g alpha by 2 to g alpha by 2. Now this can be given by theta estimate minus root under v theta hat times g alpha by 2. Yes, theta estimate plus root under v theta estimate times g alpha by 2. So this is our key percentage confidence interval using MLE, maximum likelihood estimate. Okay, so this is it. Now one of the disclaimer is that in the small sample case we can't use the property of large sample cases. That's why we can't estimate the test statistics or pivot in this way. Okay, that's why we cannot use the MLE in small sample cases. So this is all about this chapter, theory of estimation, interval estimation. I know this was quite rushed because it was supposed to be a revision course instead for the first timers. Okay, I hope I was able to give you some information and insights about how can we construct the confidence interval using pivot method or this MLE. Okay, uh, this is it. Now in another video, upcoming video, I have decided to talk about theory of hypothesis testing, chapter 8 and chapter 9 about various kind of non-parametric test. These two chapters are quite important, not only for the examinations but for its practical applications everywhere. Okay, so stay tuned for that, and thank you so much for watching this.